So I took the opportunity to add some other functions of the A-Star Pathfinding project, notably some modifiers here, into our ship prefab, which being kind of at the at the very tippy top of um, the variants for Federation ships in this Akira here, instantly gets parameters which are not changed on the Akira are going to be controlled by this. So if as soon as we add these scripts, it basically trickles down. Oh, that's terrible word choice. It basically gets passed on down to the Akira. So that's one benefit to that prefab discussion, which I have beaten as a dead horse. And so let me just tell you a little bit about these modifiers here. So paths are going to be pretty, what is it? Pretty rough without any of these modifiers. It will go from these points like this, and it won't look particularly good. So I added some modifiers here, and one is the raycast, which kind of shortens. It figures out the shortest path from these different points along the path, and then I've added an advanced smooth just to give myself a little bit more control. You can also use the simple smooth, and these combined in different ways. As you can see here, you can kind of tweak things to get, depending on what kind of game you're making, Pac-Man or something, or things that are gonna try to go tightly around corners as much as possible. Yeah, so just this advanced smooth kind of gives me a little bit more control for what to do when coming across sharp turns. Now, if you're paying attention, there's another thing that I've added here, and that's the RVO simulator. It needs its own empty game object, kind of like this A-Star Pathfinder script. And what RVO is what does it stand for? Reciprocal velocity obstacles. And if we look at this video real quick here, basically, it's really hard for these units or agents to avoid each other when there's a lot of them swarming kind of in one spot. We want them to kind of each sort of respect a little bit of their own bubble rather than trying to just bump into each other. And so this will actually look ahead and do some calculations and adjust the velocity in order to make sure that it doesn't collide along the same path. Now I also have this alternative path script, which just basically checks to see if this particular exact path has already been taken up by a unit when a new one is trying to search for a path. And so all these get me somewhat there in order to reach better movement, and I'll demonstrate real quick. But I think you'll quickly see, while they don't overlap, there is a little bit of a problem. I'll go to the scene view here so you can watch. Essentially, they're all trying to get to this really particular point, which, and each one of them is pushing the other out of the way, and so they're never really fully ever satisfied. They keep trying to go to this spot, and they never really, well, I guess this guy did, but now none of the others will ever reach it. So what can we do about this? And the answer is going to lie in our ship manifest, or the selection manifest script. We are no longer going to, let's see, yeah, on right click down, subscribe on left click. We are no longer, we're gonna get rid of this actually, and have the call for setting a course be from this selection manager. I'm going to create a function called move fleet, and it's going to listen for a right click from the user and then send everything, all selected units in order to go to the appropriate points. And notice that I said points in plural. We are actually going to, when we right click, figure out a specific point for each one of those ships that's not the same, so they won't all be trying to go to that spot. So right now, we have every single ship trying to converge on the same exact spot, and they might be this big. And so, even if one of them gets there, the rest are going to be circling around like vultures trying to get there. Instead, I want to take this one spot that the user clicks on and give each ship its own offset little point to go toward. So it'll be relatively close to where we want the ships to go, but it will factor in how much space these ships are going to take up and where each one's position should be. I just apparently multiplied ship count, but anyway, it's going to be really important when we have a lot of ships what we're trying to move to a spot. Alrighty, so let's backtrack here. The first thing that we're going to do is figure out where is the average position of everything that is selected. So we're going to create a vector 3, going to call it average position. I'm going to set it to 0, and then I'm going to keep track of the ship count. So how many ships do we have selected? Because we might have some things in this selection that aren't ships. It's possible. I'm going to create a for each statement. And the first thing I'm going to do is try to detect if it's a ship. The best way I'm going to go about that is by checking to see if there's an engines component on that ship. If there is, it will be equal to not null. So that's just detecting to see, hey, do we have an engine script on there? And then if one of the things that we're currently searching for through the selection roster does not have engines, then its ship count is going to, we initially set the ship count equal to the entire size of the selection roster dot count. And we just detected something in this else here that was not a ship, so we're going to decrease that ship count. Now I'm going to take, next thing I'm going to do is I'm going to take our average position and we're going to add each ship's position to it. So vector 3 plus vector 3 is just all the x's are going to get added together, all the y's are going to get added together, all the z's are going to get added together. And then, to take the average, we're going to divide all these added positions by the total ship count. Actually, I need to make sure that this is by ship count. So I'll come back later and do that. So after that, we're going to find the point the user clicked on the map, and so I'm going to call that destination. And we're going to search through the raycasts in the mouse, what is now called mouse conductor. Remember, we changed the name. And look for that collider that says grid. And so, you know, the thing, one of the raycasts that's collider has the tag grid is going to be the map. And we're going to set our destination equal to that raycast hit, the point that raycast hit. And then we're going to say, okay, stop going through this for each loop because we're good now. We found it. No need to waste resources. So the next thing we're going to do here, oh, sorry, the third thing we're going to do here is determine each unit's discrete move destination / coordinate and send them there. Remember, it's going to be somewhere focused around where the user clicked, but not quite that spot for each unit, because they all can't physically fit in the exact same spot. So the first thing I'm going to do is I'm going to keep track of the non-ship count, because that's important information. And we're going to create another for loop. Now this time I'm not going to do a for each. I need to actually figure out which ship or which item in this array we're currently at, because I'm going to want things to fill up kind of in the center and then go out, and then after about 9 ships go out by sort of the diameter of the ship. Kind of converge around that point by the diameter of each ship. But then when I would say, I'm going to say that about 9, I'm going to want them after the first 9 ships that have been given a destination, I want them to go out another ring, and then another, and another, and another. So we're going to need to keep track of which item in the array we currently are looping for. And I'm sorry if that doesn't make sense, but hopefully it will when you process this. So first thing I'm going to do is, since we're going to be using the set destination function on the engine script, I'm just going to figure out, okay, does the selection roster, well, let's just get the component of engines. Now let's make sure that we're dealing with the ship by engines not equal null. If not, I'm going to say that the non-ship count is going to get added to. So this is kind of similar to what we were doing up here, but slightly different variables for different information. Just with the way that this is going to be set up, kind of needs to figure out, okay, how many of those weren't ships. Oh. And then we're going to find the displacement of the current unit from the selection's average position. Okay, so basically, how far away is this individual ship from this all the units in the selection's average position? And that's what I'm going to call my displacement vector. But what I'm immediately going to do is I'm going to normalize that so that its magnitude is 1. So really this kind of gives us more of a directional information. Like you could say it is a vector 3, but it's more kind of angular, if you were, but not exactly an angle. It's just sort of a direction. It's normalized. If you're familiar with the unit circle, it's just kind of the idea of, you know, you can put coordinates kind of in the form of in this case it's like a 3D unit vector. And it just kind of gets us a direction. And now I'm going to use a class called bounds, which basically goes through all the renders and draws a box around them, a bounding box. And then that bounding box can kind of give us some size information. It will give us a width, height, and depth. And I'm going to use the width and the depth. I don't really care so much about the height of the ship on this 2D map, because I'm trying to figure out how far to displace this unit from where this unit's destination from where the unit clicked by how big it is, because a frickin' Borg cube it's really not going to be able to get into tight spaces, and it's going to need, especially if you have multiple Borg cubes selected, it's going to need to spread out the ships from where the user wants them to, from the exact point the user clicked on the map to traverse to, that is respective of each ship's size in the fleet, because they just all can't fit, unfortunately. That's how physics and math works. So basically what I do is I go find all the renderers in each one of these ships and I encapsulate them. And then I can come back to that information later, because now we're going to figure out the proper distance to displace the unit's destination coordinate based on its size and how many other units are selected. So I'm creating this float I'm going to call the rough ship radius. And I'm basically going to take the width and the depth, and I'm going to divide them in half. I'm going to take the average between the width and the depth, and I'm going to say, okay, that's pretty much my rough that would be a rough diameter. But I'm kind of just going to go based off of radius, because I don't want things to get too spread out. I want them to be... I want the size to have an influence on this, but it's a really imperfect estimate. And so now I'm going to have this parameter called what I call an offset doubling count. And this is a little bit confusing, but basically, assuming we have a selection that's greater than 9, it's going to start doubling the displacements, because it's basically going out another ring. After the first 9 ships get the closest spots to the center, and then we go out after 9, from 9 to 18 we go out 1 ring, and then 18 to I can't math, 27 we got another ring, and then to 36 we got another ring, until infinity. Like, whatever, how many ships we can deal with here. And so, yeah, for me, I think, this is just kind of a rough guess, because I don't, I don't know, I'm just going to say that, generally speaking, you can fit 9 ships into a ring. Gosh, I really feel bad for chemists trying to figure out atomic orbitals. Okay. And then I'm going to, so then we're going to have what I'm going to call the displacement magnitude. And the displacement magnitude is just going to be, oh gosh, okay. This is where it's factoring in the first 9 ships. So, cool. The very first ship in this selection is going to actually have this is going to be 0. Interesting. Oh yeah, we got to make sure that technically we want the number of the sequential number of ships that we are currently iterating through. So if some of these items in this selection have not been ships, well, then they're not going to count in filling up this orbital. Gosh, this first ring. But notice that the first item will be the 0th item, and so this will all be 0. Even the math F to seal. So what math F to seal does is basically it's like rounding up no matter what. If it's 0.0, if it's 0.000001, it's going to round it up to 1. But if it's 0, I don't think it's going to change. I think it's just going to be 0. So so we're going to multiply the rough ship radius by this, which is going to figure out which ring are we going into. And if it's the first item in the ring, it's going to be, or the very first item in the ring, in the selection roster array here, in this selection roster array. If it's the first item, it's really item 0. And so that's going to be 0 here, and it's going to be rough ship radius times 0. So it's going to end up going exactly where the user clicked. Now, if it's the second item, it's going to be 1. And it's going to get offset, because it's in the first, this whole part right here is basically, okay, what ring are we in? And so anything after the first one is going to be in ring 1. And so that is going to get displaced by the rough ship radius. And then when you get to the second ring, it's going to be twice the radius of that ship. And so on and so forth. And now we're going to kind of position the ships kind of around that user click coordinates based off of the angle or the just kind of the angle it was, how the ship was placed around the initial average position. And so that's where we bring back, we're going to create this individual destination by, oh, here we go. Okay. There we go. There it is. Just going to make sure that I multiply these two together. Oh. Perfect. And multiply those two together because we're going to take the displacement vector and we're going to kind of position, angle this, place this, scatter this based off of the angle, sort of the angle that it was from the initial, sorry, before we clicked, the ships were scattered at different vectors relative to the average position of the fleet, and it's kind of going to preserve the direction the ship was in the fleet, was placed, but kind of bring them in more tightly. And so now we're going to take the destinations where the user clicked, and we're going to subtract this new calculated displacement from that the destination, and that's going to get us our individual destination. We can tell each one to set that individual destination. Now before I forget, I'm going to go divide this by ship count, and I'm going to name this one third. Alrighty, that was a thing. I also did some tweaking to the slowdown distance and the end reach distance, and I might want to create some on-validate functions or something that actually goes to this AI path and calculates what the slowdown distance should be in the end reach distance based off of maybe that rough diameter or something that I made, because this may vary. Like, this is kind of basically, I kind of want the end to be reached beyond just a little bit, a hair beyond the actual diameter of the ship. I don't want the ship to try to pretend like it has a phase cloak and go to a spot that it just can't reach. Basically, once it's this far away, it stops, and then once it's this far away, it slows down. And I want that to kind of automatically be calculated for me, maybe by figuring out the bounds of the ship and going from there. So let's test this. Alrighty. As you can see, it's kind of preserving the sort of scattering layout. It's bringing things in tighter, but this is kind of still going to be positioned further back, and they aren't trying to reach the same exact spot. Oh, what am I doing? There we go. Let me just try this. Let's make some more. Whoops. Oh goodness, well, some of them were initially overlapping. It looks pretend that they weren't ever intersecting. We just got a bunch of them now. And they're each gonna kind of go, yeah, there we go. We're gonna try to go more compact, but not try to reach places that they just simply cannot go. And I think I forgot to mention something. I'm adding a little bit of a fudge factor here, because, again, this is a really rough estimate of the ship radius. So we're taking the dimensions of a box and kind of thinking of it in circular terms. And so I might want to increase this, or have this increase based off of ship size, this fudge factor or something. So it's kind of really more of an art form than math. But so yeah, I'm seeing it. Things might be breaking down slightly in this huge when we get to bigger fleets. But for the most part, I'm pretty happy with it. This is a lot better than it was, where every single ship would just circle around and just go berserk forever, like a fish or a dog chasing its tail. Alrighty, in the next episode, I'm going to try to get ships to bank, and by bank I mean do this and this, depending on if they're turning. If they're going this way, they'll turn like that, and then flatten back out, and then flatten back out. And that adds a lot of really good, realistic Star Trek-y ship movement, and just it looks a lot better than just these flat turns. Just very flat. Alrighty. Take care until next time.